Hello everyone, and welcome to the second part of the introductory lecture on geodynamics and modeling. In the previous lecture, we've discussed the applications of modeling to understand the dynamics of the Earth. And here you see an example of a convection model with plates that is being used to understand the internal dynamics of the Earth over the geological scale. To build such a model, it's essential to realize that we need to rely on physical principles, but we also need to use numerical methods to find the solution to a convection problem, for example. Here's an example of equations. For such type of models, we need to couple mass conservation with momentum conservation here in 2 dimensions and energy conservation. What is important to realize right now is that these are very specific forms of conservation equations, including several assumptions. So for example, here, incompressibility of the flow. Here there is no inertia, but it's linear momentum balance. Here we have a gravity term included, and the energy conservation is written here with energy sources, advection flux, and diffusion flux. So what matters here is that all of these equations are partial differential equations, and it's important to realize they are all built on some balance law. So last week we've discussed the balance law, and we took the example of the gray box here, which would be a one-dimensional element inside a medium. This element has a side delta x, and it has a flux on the west side and a flux on the east side. And what we did with this little example, we've derived a basic conservation equation. So if we want to change the value of an equation of a field in this box, for example C, if we want to change the value of C in this field, we need to introduce the balance of the flux. So for C to increase, we need to inject more from the west side, for example, than we extract on the east side. So that led us to this type of expression where the rate of change of C is proportional to the divergence of the flux dq dx. Now, to solve different types of problems, such as an advection-dominated problem, a diffusion-dominated problem, or a problem of wave propagation, we always need to refer to this equation, but we need to specify the flux Q. For the advection-dominated problem, the flux will be proportional to C and to the velocity. For the diffusion problem, the flux is proportional to dc dx, and it's multiplied by the positive constant and minus sign here. For the wave propagation problem, the rate of the flux is proportional to dc dx here. So how to deal with all these partial differential operators? What we do in this lecture, we use a central finite difference approximation for spatial derivatives such as df dx here. So df dx will be approximated by the difference between f evaluated half a delta x away to the right minus f evaluated at x minus half a delta x away to the left. And this will be our way to approximate spatial derivatives. So by doing this, all the partial derivatives become differences and divisions, which is very nice. Here you see a 1D axis where the stars here are representing the flux points. So we have here 6 flux points along this 1D axis with 6 stars. And The dots here are centroid of each of the model cells. We will have dq dx located at each centroid. So here we have 5 points containing dq dx on that example. The field C is also located on the centroid, but we have included 2 extra points. The C1 is located half a dx away to the right of the model boundary, and the second additional point, C end, is located half a dx away to the right boundary. So let's try to apply this formula to approximate dq dx. So let's approximate dq dx using a centered finite difference discretization. So we want to take the derivative of q with regard to space. Let's consider the first 2 points here of q. We have q position 1 and q position 2. How to make a central derivative? We take q evaluated half a delta x to the right minus q evaluated half a delta x to the left, and we divide it by delta x. We will get dq dx index 1. So that's how to evaluate this quantity at one point. Now we can do the same exercise for dq dx of position 2. It will be q3 minus q2 divided by delta x. And so on until we reach the end of the axis. The last value of dq dx is dq dx position 5, and it will be q of end, or q index 6, minus q of 5. What about evaluating all those points at once? Instead of doing one by one, can we evaluate everything at once? And the answer is yes. We can do it by using array slicing. So let's compute dq dx for all the points at once. For this, we need to first take into account all the right neighbors. So the right neighbor of this point is q2 until q end, which will be the right neighbor of dq dx 5. To this, we subtract all the west neighbors. The west neighbor to that point is q1. And the last one to be taken into account is q5, which is the west neighbor of dq dx position 5, the last one. So by doing this difference of two sliced array scaled by delta x, we will approximate dq dx at all points. One may also use the function diff, which allows to make the notation closer to the actual math notation. So if you do diff q divided by dx, you will obtain the same results as with explicitly making the difference here and the slicing of the array. So diff q divided by delta x will give you the same result. So what can we do with this? Actually, let's remember the balance law. This here is already a numerical approximation of the right-hand side, dq dx. So we've already treated that part of the balance law. Now, what are we going to do for the time derivative? We have dc dt, and we need to deal with this term. So now, let's think about two time levels. We have one time level here, t, with, you see, all the values of c are positioned here on the centroid. And now we consider one time level in the future at time t plus delta t. Between this time level t and this time level t plus delta t, there is a time increment, delta t. So let's make a forward Euler discretization of dc dt. So we are going to approximate dc dt by saying dc dt will be approximately equal to c evaluated at t plus delta t at the new time level minus c evaluated at the old time level divided by delta t. So in a way, if you want to compute dc dt at position 2, you would say c2 at time level time t plus delta t minus c2 at the old time level divided by the time increment delta t. So that's for the principle. Now, this expression, you can solve what we don't know in the previous equation. In this equation, what we don't know will be c at time t plus delta t. So we can solve for it. C at time t plus delta t will be c at time t plus delta t times dc dt. We're just solving for this unknown, the new value of c. Now, we can use the balance law. The balance law tells us that dc dt is minus dq dx. So what about injecting the balance law into this expression? If you do that, you can compute that c at time t plus delta t is the old value of c at time t, minus delta t times dq dx. dq dx we already know how to evaluate, and this we know how to evaluate. So that's very handy. Let's have a look at the formulation of this in terms of code. What we want to do, we want to compute the new value using the old value. And we are only going to compute the points which are in blue. It means the points which are inside the model domain. So we will compute c2 to n minus 1 from this index to that index. And for this, we use the old value in blue to predict the new ones. And we will have minus dq dx. So the new values will be on the left-hand side of this equality. Basically, what we're doing now, we will overwrite always the old value of c by new values. So let's summarize. We have this expression. The new value will be equal to the old minus d of q dx. This is basically the way to use the balance equation and solve for the new value of c. You can write it even in a concise manner here. This is equivalent to that. Here we use the operator minus equal, which means we subtract from the previous value all the time. So it's the same as overriding the value of c. So the new value is minus equal diff q dx. So the balance law is more or less treated with central and forward differences. So we can already do a lot of things with that. But if we want to solve an advection-dominated diffusion or a wave problem, we need to express the fluxes. And we have these three possibilities. So let's start with the advection flux, because it's actually a problematic case. The situation is such that if we look at the axis here, we have the value of c and we have the value of q. It's located at the midpoints between the c points. So q is here. If we want to evaluate q directly as a function of c, it's difficult because q and c are living at different locations in space. So how can we deal with that? How to compute q1, for example? Let's try to compute q1 with velocity v1. We have two possibilities to construct q1 equal v1 times what? c1 or c2? We have two different values of c neighboring the node q. So in this lecture, we'll use the upwind scheme. What is the upwind scheme? Upwind scheme means if the wind blows to the right, v is positive, the flux will be calculated using the left value of c. So if v is positive, q1 will be equal to v1 times c1. We take the value to the left and transfer the information in the direction of the wind, which is to the right. In the opposite case, if V is negative now, the wind is blowing to the left, the flux will be proportional to the right value of C. So flux will be V1 times C2. So we transfer the information in the direction of the wind. So to summarize this, we can construct one single expression to calculate the flux. It's an expression that takes into account the case where the wind is blowing towards the right, and then you would use all these points. If the wind is blowing to the right, you use from C1 to C and minus 1. That's what is shown here. But if the wind is blowing to the left, at the locations where the wind is blowing to the left, we want to select the neighbor which is located to the right. This is C of index 2 to position end. C2 to end for all nodes where the velocity is actually negative. So with this, we combine an expression which has a condition inside. If V positive, Q is V times C1 to n minus 1, plus, in cases where V is smaller than 0, the flux is V times C2 to n. With this, you can treat the advection flux. It's called an upwind scheme. Now the diffusion flux. For the diffusion flux, the situation now is ideal. Both the flux Q and the gradient of C, they are living at the same place. So if we take a gradient of C, so we make C2 minus C1 divided by delta x, the value will be located at the center, at the same place where we need to evaluate Q. So let's have a look. Q1 is C2 minus C1 divided by delta x times minus D. This ends at the correct location. So when we want to compute Q as a function of the gradient of C, it is actually convenient. If we want to compute all the values of Q now, let's say we want to update all the flux points from 1 to n, then we can use all the information from C. We can take all the C which are located to the right, 2 to end, minus all the C's which are located to the left, 1 to end minus 1. This is that expression here. Again, you can write in a concise way using the diff function. So Q can be evaluated simply as minus D times diff C divided by delta x. The last flux formulation we want to discuss is the one to be used for modeling the wave propagation. So in the wave propagation, we have the gradient of C on that side and a constant, but this is proportional to the rate of Q, not to Q. So to solve for Q, we will need to discretize the rate of Q. And this is something we did right before for the balance law. We make a forward Euler discretization of the rate of Q. So dQ dt will be the new Q at time t plus delta t minus the whole Q divided by delta t. This expression you can solve, and you will obtain that Q, the new Q, will be the old value of Q minus C times delta t times the approximation of dc dx. So here I'm using already this expression here. To evaluate this term, you can again use diff c dx. For that part, has to be multiplied by minus c and delta t. And the value of the flux is not simply equal, but it's minus equal because it is incremented at each time step of the simulation. So that's the expression now for introducing the wave flux in our simple one-dimensional code. So to summarize, we have the balance law. The balance law, we use it to solve for C. And we have this expression which includes an incrementation in time. We also know how to solve for the fluxes. In the advection case, we have Q directly proportional to C. For this, we need to use upwinding. For the diffusion, we have Q proportional to dc dx, and this is all nicely located in the grid, so no problem. And for the wave, we have also dc dx, but we have a rate of Q, so we also use a time discretization as we do for the balance law. So we basically have most of the elements, but last informations are, you need to always remember that these equations, this balance law, for example, it includes a time dependence. So since we need to increment over time, we also need to provide an initial condition. And this is what we do, for example, by defining a Gaussian profile initially. Also, the equations we use, for example, when we compute a flux, it includes spatial gradients. So we need boundary conditions to solve for the spatial gradients. We need to know what is the value of either the field C or the flux of C at the side of the box. And in the exercise, we are going to set a periodic boundary condition. And the last information to be said about that is that the numerical method we use here, it's called an explicit finite difference scheme. It will only be stable for a restricted range of time step values. And these time step values, they depend on the physics. So for the advection case, the time step value will be proportional to delta x and to the maximum velocity, absolute velocity in the domain. For the diffusion, it's proportional to delta x squared and the diffusion coefficient. And for the waves, it will be proportional to delta x and the velocity of the wave. So that's it for the lecture part. Now, what we're going to do, we will code up the solver for advection, diffusion, and wave propagation using the basic finite difference method. For this, we build on top of last week's script, which is already used for defining an initial condition. So let's finalize this exercise. Thank you for your attention.